Hey there everybody, welcome to the first video on section 7.8. As with sections 7.5 and 7.6, this section is split into two videos. One video which focuses on solving the systems, and the second video which focuses on the pictures you get from systems like this. So this is the video that shows you how to solve systems like this. Let me say up front that the more of these videos I make, the sadder I become that we aren't in class. I don't know about you people, but I really enjoy going to class. I really enjoy talking to you face to face about this material. So the longer this quarantine drags on, the sadder I become about it. And as I was thinking about that, I actually was reminded of a YouTube clip that I saw. Let me show it to you. This is me turning on my laptop here. That's what it's like.
Stay on. Hey, Miss Potts. If you find this recording, don't feel better about this.
That spaceship, like my office.
Just for the record, being adrift in space with zero promise of rescue is more fun than it sounds. Food and water ran out 4 days ago.
Yeah, like going to Hy-Vee, right? Food and water have run out, along with toilet paper. I wonder what Iron Man did with no toilet paper up there. Anyway, I don't know if there are panic runs on toilet paper in his spaceship. But anyway, that's sort of what I feel like the longer I make these videos. Anyway, back to this one. So the point of section 7.6 is to think about what happens when you get repeated eigenvalues in these systems. So just to recap what we've done, we know what to do when the corresponding matrix has real, distinct eigenvalues from section 7.5. From section 7.6, we know what to do if all of the eigenvalues are distinct and you happen to get complex numbers in there. So what do you do if the eigenvalues aren't distinct? Okay, so just to reset that, from section 7.3, we know that an n by n matrix has at most n eigenvalues. And in all of the examples we've done so far, that at most was actually just an equal. So a 3 by 3 matrix turned out had 3 eigenvalues. A 2 by 2 matrix turned out had 2 eigenvalues, and so on. These values, though, come from solving an n-degree polynomial. So n-degree polynomials sometimes have fewer than n solutions, right? Like with a quadratic, sometimes you get just one solution that's repeated twice. So the question for this section is, what if you're trying to solve a 2 by 2 system and there's only one eigenvalue? So here's an example like that. If you start without matrix notation and then make the translation, here it is. The eigenvalues of that matrix are 2 and also 2. 2 is repeated. And there's a corresponding choice of eigenvector. So how do you solve this system? Well, if you think back to chapter 3, it seems like there's an avenue available to us. So sections 7.5 and 7.6 have mirrored chapter 3 fairly nicely, right? So can we just do this? This is what we did in chapter 3. We said, well, I got my first exponential, and now in this case times an eigenvector. Can I just repeat that but with a t on there? Doesn't that seem like the natural thing to do? And if we were in class, I would ask you if this is what we should do, and all of you would say yes, and you'd fall right into my trap. But in this case, I have no trap to spring on you because this is a pre-recorded video. But spoiler alert, you actually can't do this here, unfortunately. And it's kind of strange that you can't, but basically there's some linear algebra issues under the hood that we don't get into here. But basically you can't just slap a t on things now, unfortunately. So just to show you why not, let me just consider what happens if you do this. So if this is the general system here, that means that for any C1 and any C2, I'm supposed to get a solution. So let me just consider what happens when C1 is 0 and C2 is 1. So let's imagine killing off this first term, and the second term just has the negative 1, 1, t e to the 2t. Okay, so what would that look like? That would mean that x1 would be the top coordinate, and x2 would be the bottom coordinate in this setup here, right? In this matrix here, this vector. So the top coordinate is negative 1 t e to the 2t. The bottom coordinate is 1 t e to the 2t. Again, assuming c2 is 1. So x1 is the top, x2 is the bottom, and that's how I get these concrete functions here that together should be a solution. So in order for those two functions together to be a solution, we would have to be able to substitute both of these functions into the original system. And here's the original system again. So let's plug these functions in and just see how it goes, So x1 prime, that's supposed to be x1 minus x2. Is it? x1 prime is this. x1 minus 2, question mark here, right? x1 minus 2 is definitely this, which simplifies to just this. Negative 2 e to the 2t, right? Negative 2 e to the 2t is not itself minus e to the 2t, right? That's just not true. So all that to say, if you do this thing that from chapter 3 you should be able to do, I guess, right? If you do it, you just end up writing down things that aren't solutions. And that's a problem, isn't it? If you're supposed to be providing solutions to the system. Okay, so all that to say, if you just write this down, you will run into contradictions like this, right? Negative 2 e to the 2t minus e to the 2t is just not the same thing as negative 2 e to the 2t. There's no debate there, is there? So all that to say, you just can't do that. You collapse into contradiction. So womp womp, sad face. What do you do, though? Do you just give up and say, well, repeated eigenvalues are just something I can't handle? Of course not. We're resilient, aren't we? Right? We don't give up in the face of challenges like this. We self-quarantine for 2 months to figure it out, And here is figuring it out. So let's let A be a 2x2 matrix with a single eigenvalue R and corresponding single family of eigenvectors represented by V. Notice this theorem only handles a 2x2 case. Okay, so that's not an accident. But anyway, I'm going to let eta be a generalized eigenvector of A. So here's where I die a little bit inside. I would like to explain more about what this is, but for now, we will just have to take it as a black box because we're paring back material since we're not in class. Let me just show you what Wolfram does here. Okay, so once I finish saying this theorem and go back to the example, Wolfram just spits this out, and I'll just show you how that happens. Anyway, the general solution of the DE system is this. I have C1 eigenvector e to the eigenvalue t. This is completely expected and normal, right? We already knew that from previous sections. But now notice I don't just have C2 eigenvector t e to the RT. I actually do have that, but then I have this extra term here. You have an extra eigenvectory sort of thing with no t on it times e to the eigenvalue t. That's how you handle a 2x2 system with a repeated eigenvalue. So here's the example revisited. Again, has one eigenvalue, one corresponding choice of eigenvector. The corresponding generalized eigenvector, it turns out, is 1, 0. Let me just show you that. If I go to Wolfram and ask it for eigenvalues, I got to remind myself what this matrix is. 1, negative 1, in row, open new row, 1, 3. Okay, Wolfram says this. Result, only a single eigenvalue. There's its eigenvector. Oh, here's a generalized eigenvector, it calls it. So Wolfram just gives that to you. And again, if we were in class, I would say more about what this is. But for now, let's just accept this. This is a linear algebra thing that we are willing, I guess, just to be handed by the computer. So let me hop back to the example now. So given that, I can just rip the formula straight from the previous page. X, bold X of t is C1 eigenvector e to the eigenvalue t plus C2, and then big parentheses here, same eigenvector, now a t slapped on, plus 1, 0, that generalized eigenvector, no t here, e to the 2t. If you want to write that without matrices, then as always, x1 you just read across the top, so negative c1 e to the 2t plus c2 negative t e to the 2t plus c2 is still here, right? c2 1 e to the 2t, and then x2 you read across the bottom, c1 e to the 2t, and then c2 t e to the 2t, and there's a 0 there. So anyway, that's how you solve systems like this. So here's an exercise for you. Solve this initial value problem. Write your answer in matrix notation and also without matrices. Pause the video, and I'll wait for you to come back. Okay, so assuming you're back now, I, like Tony Stark, is so happy to see you, right? After you've found my little spaceship floating in nowhere. Anyway, the answer is this. So hopefully you got something like that. So this system here has only one eigenvalue, therefore only one representative of eigenvector. So you have to plug into this kind of thing here, right? So your initial answer should have looked like that. That's your general solution. This general solution, though, as always, has constants in it. So hopefully you remember that, oh, with an initial value problem, I actually have to nail down those C1 and C2 values. We've looked at an example like that before, so hopefully you can reference back to section 7.5 or whatever. But again, you just solve this guy first, and you get something that looks like this with C1 and C2, and then after the fact, you come back and say, oh yeah, when t was 0, x1 was supposed to be 2, and when t was 0, x2 was supposed to be 4, and you end up with these two separate functions, not written with matrices. You can write them with matrices if you would like, as we have in the past. Okay, so let me conclude this by talking about what happens with larger systems. The main theorem of the section only handles 2 by 2 matrices. What if you have a 3 by 3 matrix? What if you have a 6 by 6 matrix? Whatever, right? So a 6 by 6 matrix would mean 6 functions, 6 equations, right? So you have 6 unknowns with 6 differential equations. Here, 3 unknowns, 3 DEs, etc., right? How would you handle that? Turns out we're not going to, really, okay? Turns out it's like really, really hard. Much harder than you would expect if you just kind of naively traipsed into this section after reading through chapter 3, right? Chapter 3 don't care how big the system is, right? You can handle anything with any number of repetitions. It's just a matter of slapping more t's on that thing, right? So chapter 7, though, does care quite a bit about these repeated eigenvalues, and there's just not really a good way to handle them. So if you want to get an idea of how hard that is, you can look at number 18 in the book exercises. That problem deals only with the case when an eigenvalue is repeated 3 times. So it doesn't even try to deal with a general case of repeated 5 times or whatever. And even that exercise is like pretty hard. You know, it's like all up in your face with how obnoxious it is. So basically the problem here is like a 6 by 6 system could have only, like it could have one eigenvalue that's repeated twice and another one that's repeated 4 times. And the one that's repeated 4 times, that might only have one family of eigenvectors, or 2 families, or 3 families, or 4 families. Like it's just, you know, it's just a mess. Anyway, the linear algebra is a mess. So we're not going to deal with larger systems with repeated eigenvalues. Again, unlike chapter 3, this is kind of unsatisfying. It's unsatisfying to shrug because things are hard, you know, or at least it's unsatisfying to me to do that. In chapter 3, we could do it all, couldn't we? But we've lost some of our power here. Systems are just harder to solve than just the higher order linear DEs with constant coefficients from chapter 3. All right, so that's the end of this video. On the next video, we will just briefly cover the slope field pictures you get with repeated eigenvalues.